Let's take a look at another example from Introduction to Stoichiometry, BCA charts. Again, it's a method for keeping tabs on chemical quantities in a chemical reaction. So looking at what we are given, we've got calcium hydride reacting with water. We're going to make calcium hydroxide and hydrogen gas, H2. Just looking at the equation here, remember what the parentheses tells us. We have a hydroxide ion, polyatomic ion. Its formula is OH minus. It's got a minus charge. There are two of those for every calcium in the formula unit, and that's because calcium is a +2 ion. So I like to balance these visually just by showing how the reactant atoms would rearrange into product. So I'm going to try to build a unit of calcium hydroxide by taking a calcium atom. I'm going to need to pull in an oxygen and a hydrogen to make a hydroxide ion. And I realize I'm out of oxygen on the reactant side of the equation. So I'm going to back up a second and realize if I need more oxygen in my product, the way I would solve that problem is by doubling the water molecule. That's the only reactant that has oxygen in it. So let me do that visually. And now I'm going to, again, try to rearrange my reactant atoms into product. So here comes an oxygen and a hydrogen to make a hydroxide ion. And I'll do the same over here. So now I have one unit of calcium hydroxide. The other thing I have to build are hydrogen molecules, which are always H2. So notice that I actually have enough hydrogen to make not one, but two hydrogen molecules in the product. So that tells me I also need a coefficient of 2 in front of H2. Now, getting to the stoichiometry, we want to know how many moles of hydrogen gas and calcium hydroxide would be produced, those are my products, if 5 moles of water reacts. That 5 moles of water is going to be my given. So I'm going to go ahead and start and fill out the before line before I do anything else. So my given is that I'm going to have 5 moles of H2O. And then I need to think about my coefficient ratios reflecting the mole ratio. So even though we normally don't write them, I'll go ahead and write a 1 in front of these two quantities because there's an implied one there. Our mole ratio should reflect that ratio. So this one's a little different in that I'm starting with 5 moles of H2O, and the ratio here is 2 to 1, meaning the reaction ratio should occur in a 2 to 1 ratio, meaning I actually need half as much calcium hydroxide as I do water. So the mole amount that would perfectly react with 5 moles of water is actually going to be half, 2.5 moles. And of course, before the reaction starts, we don't have any product. So I'm going to go ahead and write in 0 moles on that side. Now, the way we represent the reaction, we think about all that starting stuff that we had being converted into product. So my change here is subtracting. We're going to assume every little bit of reactant gets converted into product. So on the other side, I need to think about how many moles of calcium hydroxide would be produced. And I need to go back to the coefficients. These have the same coefficient, right? 1 to 1. So they should react in a 1 to 1 ratio. The same amount of moles of calcium hydroxide should be converted into the same amount of moles of calcium hydroxide. I want to make sure I said that correctly. Calcium hydride, 1 mole, converts to 1 mole of calcium hydroxide. In other words, the same mole amount will be produced over here as is reacted for the calcium hydride, CaH2. So I'm going to go ahead and add 2.5 moles as the change. That's what gets created in the product side of the reaction. Now here, I can do things a couple of different ways. I've got a 2 and a 2, so those should react in the same mole ratio. So I should produce 5 moles of H2. Now notice, I can also look at it this way. I know that this is a 1 to 2 mole ratio, and I have 2.5 moles to start, so I should make twice as much H2 in the course of the reaction. So what do I have left afterwards? Again, we're taking this special case where we use up every last bit of reactant. These go to 0 moles. That won't always be the case going forward. That's something that we'll look at later this week. I'm going to make 2.5 moles of calcium hydroxide, and I'm going to make 5 moles of H2. Okay. Now, just a sneak peek of where we're going to head with this. Right now, we're working in mole quantities, and the numbers are working out quite nicely. We know that we can't measure something directly in moles in the lab. You have to put it on a balance and measure its mass. Then we use molar masses to calculate how many moles are present. So one kind of neat thing that you can do in this problem to make sure that you've done it correctly is you can go back and do conversions from moles to grams at each of these steps. And you can get a grand total of grams here. And that would be your total mass of reactant. We know in a chemical reaction that mass is conserved. So then if you go and look at what you have in the after line and convert those to grams and add them up, you will find that that gram amount is also the same. If you want to try that, I'm going to give you the number, and then we'll come back and look at this in more detail later. But if I add up these mole amounts and I figure out how many grams I start with, you should find, if you go to 1 decimal place, 195.3 grams. That would be figuring out this gram amount, adding it to that gram amount. And sure enough, if you do the same over here, you will find 195.3 grams of product. So all of those atoms that you had to start ended up in the product, so it should make sense that those gram amounts do work out. I'll give you one more thing if you want to try this again and kind of check. The individual gram amounts for these, if you do the calculation, it's 105.2 grams is equivalent to 2.5 moles of calcium hydroxide. 90.1 grams is in 5 moles of water. Over here, this actually ends up being 185.2 grams, and this ends up being 10.1 grams. Again, the total mass to start equals the total mass to finish because mass is conserved.